We will wait couple more minutes for people to join, then we can start. Okay, let's start. So this is Applied Thermodynamics course, a problem solving session for week 2. So the course instructors are Professor Niranjan Sahu and Pranab K. Mondal from IIT Guwahati, and I am Bharat Aditya, a PhD student from IIT Madras. So this course this week is deals with Rankine cycle, and you also have Carnot cycle. We'll see the comparison of both, and we'll see some problems and some MCQs over that. We'll first see a review of uh, what is Carnot cycle and what is Rankine cycle before starting the numericals. So ultimately, thing is, any cycle you need some output. That's what you decide. So you use some cycle to, or a system which runs in a cycle to get your desired output. It could be any form of electricity in thermal power plants or the other power plants, or in terms of work. In sense, you use engine in cars to move, so that is a form of work which you get. Or it can be cooling or heating. It can be air conditioners or refrigerators. It all runs in cycle. So you have different cycles operating. How will you quantify this? You have then it's like you have a term called efficiency. You use that to see how much are you getting from the input which you are giving. That's one thing. But there's another thing where how much maximum you can reach, or how much is the maximum possible which you can get from a cycle. So the same question was asked by Sadi Carnot, who is a French scientist and engineer. So he asked, what is the maximum possible amount of work which I can get from a cycle or system. So to answer that question, he came up with this process, which has two expansion and two compression process. So that is represented as a you will see in a TS diagram. So it has two isothermal process and two isentropic process. So this is all reversible. So he considered a cycle which is totally reversible and which has less entropy generation. There is no friction or anything. It's total ideal cycle which he considered, and he said there are two statements that a temperature Carnot cycle operating between two temperature levels will all give you same work, or they will have same efficiency. And second conclusion which you can take from Carnot cycle is that any other cycle will not have greater efficiency than the Carnot cycle. So Carnot cycle will have the maximum efficiency. So those are the two statements you can conclude from the Carnot cycle. So you see the operation of Carnot cycle, you have four processes. You have first an isentropic compression. So it's a reversible adiabatic. So there is no heat transfer. So you have a pictorial view of what's actually happening. You have a piston cylinder arrangement. So you are compressing the you're compressing the gas. So you put assume there is a heat transfer can happen only at the crown or the bottom end of the piston. So you're compressing the cylinder, so there is being work being given to the system, so there will be work happening, and then after compression you are transferring heat during this at temperature TH. So there is a heat transfer, you are giving in heat, and there is also with heat addition, isothermal heat addition, there will be an expansion as well, compression as well. There will be isentropic compression, then there will be isothermal compression. So during that process there will be heat addition as well. So two things happens. The compression goes on, and while you are adding heat as well. After the end of a heat addition, you do a isentropic expansion. So there is a reversible adiabatic. So there you remove the heat source, you insulate it, you try to expand it. So the piston will expand, and then you keep this in contact with the lower temperature heat source. So there will be heat rejection to that lower temperature heat source. During this process also the piston will continue to expand. So those are the four processes. There are isentropic compression, then isothermal heat addition, then isentropic expansion, then isothermal heat rejection. Those are the four processes. If you see, this can be achieved in a different way also. You have two turbines and two compressors. A similar process. You have compression, and then this turbine, which also has the first one will be insulated. You should not have any heat transfer. So isentropic compression, you insulate it, and then you send the fluid to the next compressor. This will have heat addition. Then during the compression process, it also have heat addition. Then you send it to turbine. A similar process, which I told in expansion, it's stored in a turbine form. So the problem with Carnot cycle is here, if you can see, I have shown two processes. Assuming that I use this Carnot cycle is irrespective of fluid, whatever fluid you may use, it depends only on the temperature levels. So that's the efficiency what you get is irrespective of whatever fluid you use. So now we assume we are using a steam power plant. We are running it in terms of Carnot cycle. So what maximum you can do is you put it inside the dome, because you need an isothermal process. If you put it inside a dome, you will have isobaric. It will become isobaric as well. So this is the process represented inside the vapor dome. So now what's happening here is you have this is the vapor dome for water. Now we are assuming a steam power plant. So this is for water. So you are compressing it. So this compression is in two phase, and then you are having heat addition, and then expansion, and then heat rejection. If you see, if we are able to practically build, so that's a hypothetical case, we are able to build Carnot cycle. So what all problem can we have? The first thing is you have a temperature. As I told before, the Carnot cycle efficiency depends upon, or the maximum work you depend upon the temperature levels in which you are operating. So normally, how do you get heat addition? What you get energy from? You have to give some energy. So heat is given by burning coal or a nuclear reactor, or burning natural gas and other. You burn them and you get energy from them, and you give it to the power plant. They boil water. So that is the process happening. If you see the temperature of the coal burning and this thing, the temperature there will be a lot higher. If you see this vapor dome for water, so this critical point, the topmost point of the vapor dome will have a temperature of 373, and the maximum pressure it can have is 220 bar. So that's the pressure, the critical point for the water. So when it operates below that, so you're though the heat source is at a higher temperature, you're not fully utilizing that source. So that's one problem if you put it inside the vapor dome. So your heat source may be at a higher temperature, but still when you are operating inside the vapor dome, your temperature difference between the heat source and the higher temperature operating temperature is very large. So that is large irreversibility which will take care, and you are not fully utilizing that heat which are available for you. And the second is two-phase expansion and compression process. So two-phase expansion, though the turbines may be efficient, it will create troubles like you cannot, the two phases will the liquid generally will go and impinge on the turbines, and it can erode the turbines. So that can happen in a turbine. If you see in a compressor, you can liquid is very hard to compress, and you can have problems like water amber and cavitation and other stuffs. So these are all practical problems which you can face when you are building if you are able to build a Carnot cycle. So so one of this thing can be said, you can say that I'll put it above like this, which are shown in the figure 3 below. So you are able to overcome the two-phase cases also, and the other is the temperature. You are utilizing the temperature, but the problem here is your pressure which you are operating will go up very large. As I told, the critical pressure is 220 bar. The 220 bar is a very big pressure, and if you are operating at a higher temperature, your pressure is is becoming even higher. So that can be another problem which can happen here. So this is the basic idea of the Carnot cycle, and what practical implication it can, difficulties it can have if you are able to build the Carnot cycle. So, and I have given a efficiency formula for the Carnot cycle. So efficiency is defined as the work by the heat which you give in. The work can in a cycle, so the net work equals the net heat transfer. So W is 1 minus Q out, Q in minus Q out by Q in. This W here is the W net. So you can say Q in minus Q out by Q in is 1 minus Q out by Q in, and this Q is directly is proportional to the temperatures. So you can write temperatures in terms of heat. So 1 minus Q out by Q in will become 1 minus TL by TH. So lower temperature there is heat rejection, so TL, and higher temperature you are having heat addition, so TH. So that's the efficiency formula, which you can have a maximum efficiency which you can achieve between two energy levels. So this is a cycle which we can compare the other cycles to see how efficient the cycle is. So that is the basic idea of a Carnot cycle. So moving on, we have a Rankine cycle now. So steam power, for steam power plants we have a Rankine cycle. So this too has four major components. You have a pump, you have a boiler, you have a turbine, and then a condenser. So these are the four processes, four major components. And if you see, pump and turbine have isentropic expansion and compression. So they operate in reversible adiabatic mode. Then you have a boiler and condenser. These are happening at constant pressures. If you see in a Carnot cycle, we said that this is a isothermal processes. Heat addition and heat rejection happens in the isothermal processes. But if you are inside two-phase dome, isobaric, you can call it isobaric as well, because the pressure and temperature will remain, the lines will remain same for a pure fluid. So in this case too, we are just converting that isothermal to isobaric process. So heat addition and heat rejection are isobaric processes, and then reversible isentropic process for pump and turbine. So I have given each of energy balances and entropy balance and exergy balance, just to give you an idea what's happening for each component. So for each component, your mass, it's a steady flow process, and your mass is all constant, what is coming in and what it's going out. So there is no accumulating or reduction in mass in each component. So the mass is constant in each of it. And then you have a first law balance. You will get from the steady flow energy equation, you can get the second equations. So if you say for boiler, you have inlet of 0.2. So you have M2H2. So net enthalpy coming in equals the energy which you given, heat given, equals to M dot H3. So which goes out. So that's from energy balance you will get that. And same, if you convert it to and do an entropy balance, you'll get an entropy which is coming in, the entropy which is generated due to the heat transfer, Q in by Ts, and plus the entropy generated in the boiler equals the entropy which is going out. You can use this to both second and third equation to generate the exergy equation, exergy balance. So we can say that exergy which is coming in, and exergy which is coming in from mass entering point 2, the exergy with the heat transfer equals exergy lost in the boiler and exergy which is going out. So similarly, I have written it for each of the other components, similar expressions, and I've shown a TS diagram for a Rankine cycle. As you can see, 1 and 2, S is the ideal isentropic process, but the pumps and turbines are not totally isentropic. You define isentropic efficiency, how much they deviate from the ideal case or a reversible case. So those are represented using the dotted lines, and you have both work we are giving in work for the pump as a electrical, the energy you convert it to motor and you drive the pump, and that is one work coming in, and the other work out is from the steam turbine. Though these are 4 major components, you will have other components as well. The boiler, you are getting you're burning some kind of quantity like coal or something to generate heat which is transferred to the boiler, and condenser, you will use another water or something to cool the condenser, and you will take it to a cooling tower in which you will cool that water. If you don't want to, you cannot just directly send that water away, so you'll put it into a cooling tower, and then you'll cool the water, and you can recirculate that to cool the condenser. So those are other major parts which will come in with the Rankine cycle, but the focus on the cycle, you will have only the 4 major components which are the corresponding process are represented in the TS. So why I have given in terms of exergy is it to understand to better understand the process. Exergy gives you the maximum amount of exergy, maximum amount of work which you can get from a source. So here your Q in is the energy which you are giving in, so that will have some amount of exergy. So that is the maximum exergy amount of work which you can get from that source, and using that we can calculate how efficient is that, and you can compare it with the Carnot cycle, because the Carnot cycle being giving the maximum efficiency, the work given by the Carnot cycle is the maximum exergy which you can obtain as well. So moving on, we will see some numeric multiple choice questions. It's similar to the assignment problems, and then I have some numericals as well solving. We'll see that as well. So starting with, we have you can type the answer in the chat box if you want, and we can have a discussion of that. If you have any doubts, you can ask me at that time. So the component of the steam power plant in which the working fluid vaporizes is your 4 major components of the Rankine cycle listed: boiler, condenser, pump, turbine. So the component where steam power plant, where the fluid is vaporizing, it's from liquid to vapor, it's converting liquid to vapor. So boiler, that is, yeah, there's a fairly simple question. It's a boiler. So moving on, which of the following is not a primary goal of subsystems associated with steam power plants? Which of the following is not a primary goal? You have steam power plants which the out of listed, that is not your primary goal. That's not your main goal. So A, convert shaft power to electrical power. B, convert electrical power to shaft power. C, supply energy to vaporize the power plant working fluid. D, provide condenser cooling water.
C, sir. Supply energy to vaporize the power working.
No, it's convert electrical power to shaft power. So the others are major. You can say think you are getting work. You can also drive that pump as well. but that is an additional requirement which you have. If you see that out of the except B, the other threes are what the major requirements are. You convert shaft to electrical power, that is your output, that is what needed. You can use that to drive the turbine, to drive the pump also, a small amount. You can think in that point of view, and you need to give you need to give energy so that the cycle will remain. You cannot generate work without giving you input. So C is required. That should be primary goal, because that is needed. And condenser cooling, without rejecting heat you cannot run the cycle. So threes are the major components of the cycle: generating work, and giving in input, and rejecting heat. All three are required for a cycle to be in operation. So that's why A, C and D are required. So B is the option. So moving on, we have the component of a steam power plant that requires a power input, and a component in which the working fluid rejects energy by heat transfer are dash and dash. One which requires power input, and one which rejects heat, out of the four components. Yeah, I think a simple question. So the answer is option B, because pump you are giving in work, and condenser here, there you reject heat. You use a cooling water line, or uh, uh, reject it to ambient, to you do it in condenser. So working fluid rejects energy in condenser, and a power input is required in pump, because turbine generates power, and boiler you take in heat. So the left out is pump and condenser.
Sir,
Yeah.
in the pump only supply the water only, sir. How to
No, pump.
supply the power?
Your one of the input is water, but how do you increase the pressure? How do you pressurize the water? Send it to boiler. You cannot directly just pass the water to the boiler, right? So you have to give in some amount of work. What you do is you give in electrical energy. It will drive the motor. The motor will drive the pump. Okay, so that's why you give in power, because without power the pump cannot run. So the options are pump and condenser. Okay. So next question is, which of the following component of steam power plant is with the largest exergy destruction? A, pump; B, condenser; C, boiler; and D, turbine. Largest exergy.
Boiler.
Okay. The answer is boiler, because you have a high temperature source, and you may not be fully, because the temperature at which the water is boiling and you're taking it to that, till that point there is a huge temperature difference. You can think in that point. So your heat transfer is happening at a larger temperature difference. So you can say there will be a large irreversibility happening. So it will generate large exergy destruction. So hence boiler. So match the following case. You have given a boiler, turbine, condenser and pump. In you have an options for what are the processes they are happening: reversible adiabatic expansion, constant pressure heat addition, and reversible adiabatic compression, and constant pressure heat rejection. So each components are operating at different processes. So you have to list out and match those processes and the component. think it's easy. If you want, I can go to the back to the slide and show you. We have 4 components: boiler. If you remember, boiler and condenser are rejection and heat addition components. So, and turbine and pump are work generating and work consuming components. So, if it's adiabatic, there is no heat addition or reduction. You can say, so boiler first is constant process pressure heat addition, because you want heat to vaporize the fluid. So boiler is 1 is B, and then turbine, there's a reversible adiabatic expansion. It's expansion happening turbine. You're generating work, so fluid will expand and drive the turbine. So 2 is A, and then 3 condenser, you are rejecting heat. So constant pressure heat rejection, D. Then pump you are giving in work, so and you're compressing, so reversible adiabatic compression. So the answer is option A. Okay, so the next one. So in a vapor power cycle, enthalpy of steam at inlet and outlet of turbine are 2800 kilojoule per kg and 1800 kilojoule per kg respectively. So a vapor power cycle is what Rankine cycle. Enthalpy of steam is given at inlet and outlet. If the pump work is neglected, so you are neglecting the pump work, find the specific steam consumption in kg per kilowatt hour. I hope what you remember what is specific steam consumption is the amount of water or this thing required to generate per kilowatt hour of power. Okay. So we'll see how to solve this. The answer is 3.6. So you know that the total net work is the turbine minus the pump work, and we know that the question they are asked to neglect the pump work, so that pump work can assume it to be 0. So the turbine work is the enthalpy is given 2800 kilojoule per kg and 1800. So the difference of that is you will get 1000 kilojoule per kg. So this is in kilojoule, and you want it to in hours, so you multiply by 3600. It will be in seconds. You for converting it to hours, you multiply by 3600. So 3600 by W net. So 3600 by 2800 minus 1800. So 3600 by 1000, you will get 3.6. So the specific steam consumption is 3.6. Okay, I hope this is clear.
Yes.
Okay, so moving on, we have in a Rankine cycle, consider the work done by turbine during steam expansion is 3500 joules. So we have work done in the steam Rankine cycle. They have given work done, it's 3500 joules. Note that the pump work to feed back the water into boiler is 1300 joules. So the work ratio will be okay. We'll see the solution. So work ratio is defined as the ratio of net work output to the work done in the turbine. So that is what the definition of work ratio is. So it's equals to W net by W in turbine, or we can say just a ratio to see how much work is generated and how much work is consumed in the process. So R, you can say it is W turbine minus the pump work divided by the turbine work. So it will come out to be 1 minus the pump work by turbine work. So the fraction of work in the turbine which is consumed by pump will define the work ratio. So if that is large, your total work net which you are getting will go down. So the cycle, if your total work you're generating which is will also go down, the efficiency will also come down. So if you can see, you have given the turbine work is 3500 and the pump work is also is given as 1300. So you can substitute that 3500 minus 1300 by 3500. So it will come out to be 0.628, which is close to 0.63. So the answer is option D. Okay, so the next question is, the Rankine cycle is considered as an ideal cycle for steam power plants owing to the fact that, so Rankine cycle is considered ideal cycle for what of the reason? So that's the question. A, water enters pump at unsaturated state. It produces maximum turbine work. It includes reversible processes. It does not allow isentropic expansion. I think just seeing ideal, we would have gotten fair idea what is should be the answer is. The Rankine cycle is said ideal because of what? A, water enters pump at unsaturated state. B, it produces maximum turbine work. It includes reversible processes. It does not allow isentropic expansion. I hint is you can compare it with the Carnot cycle. That is also an ideal cycle. I said that Carnot cycle consists of all. So the answer is option C, reversible processes. As a Rankine cycle, the ideal Rankine cycle will not have any irreversible process. The compression and expansion also is considered reversible processes. The deviation is that the actual turbine and compressor may not be reversible. It will not give you a reversible adiabatic expansion or compression. So you take it into account by using an isentropic efficiency. But the ideal Rankine cycle will have all reversible processes. So the answer is option C. So the next one is, consider the following statements regarding the Rankine cycle for steam power plants. So Rankine efficiency of steam power plant is higher in the winter season compared to the summer season. So that is statement 1. The statement 2 is, this high Rankine efficiency in winter season is because of the lower condenser temperature. So that is statement 2. Is it true, or the statement is correct or not? That is what has been asked.
I think both are correct, sir.
Yes, both are correct. The reason being, at winter, the reason is given. The second statement is the reason. The first statement is the effect which you see, and second statement is the reason. Because your temperature is lower, you can think it in the point of exergy also. Exergy states that you have a heat source, the maximum work which you can get from doing a reversible process till the dead state. The dead state is that environment condition which you have. So this dead state itself is going down, because in winter that environment temperature is itself going down. So you are getting more energy out from that a normal temperature to the lower temperature. You are getting that much temperature difference. So you can get some work out of that. So you can think in that point as well. Or you can think it in terms of Carnot also, the two temperature levels. So those they are depend on the two temperature levels. If one of the temperature is kept constant, the other is taken lower, so there will be bigger temperature difference. So you'll have more work. So both 1 and 2 are correct. Sorry, this I have to check. I think I made a mistake. This is both are correct. Which one of the following statements is correct? Uh, Work ratio and efficiency of Carnot cycle is higher than the Rankine cycle. Work ratio and efficiency of Carnot cycle is lower than the Rankine cycle. Both the Carnot and Rankine cycle have equal work ratio and efficiency. Work ratio of Carnot cycle is low and the efficiency is high in comparison to the Rankine cycle. So here we have been asked to compare Carnot cycle and Rankine cycle. I hope you remember what is work ratio. Work ratio is the net work by turbine work, the expansion work which you are getting, and net work is the expansion work minus the compression work. So that is the work ratio, and the other term is efficiency. So we have to compare both. If you remember the first slide, we were given the Carnot cycle. If you remember that, I think it will be fairly easy.
I think it is our answer. Work ratio of Carnot cycle is low and efficiency is high in comparison to the Rankine cycle.
Okay, the answer is correct. The work ratio of Carnot cycle is low, and the efficiency is high in comparison to the Rankine cycle. I think it can be better understood if you see that. I'll just give you that slides. You can see. If you see this temperature, it's also, if you see in it, better if you see it in enthalpy and pressure temperature diagram also, you can see there will be a larger enthalpy difference in compressor and compared to the pump. So it will take much more energy in terms of in Carnot cycle to compress. So the back ratio, work ratio will be larger in Carnot cycle. So work ratio in Carnot cycle will be low compared to the Rankine cycle, and efficiency for Carnot cycle will be the highest. Any other cycle cannot beat that. So efficiency of Carnot is high in Carnot cycle is high in compared to the Rankine cycle. So the answer is option D. So what I've taken is I will see some problem solved. I've taken a Carnot steam cycle, which I've already discussed in the first slide. So it's inside the two-phase dome, and we have two temperature levels. And each temperature level is one is 300 degrees Celsius, and the sink temperature is 20 degrees Celsius. So that is given, and we are asked to find out what is the thermal efficiency ratio of turbine work to compressor pump work. So the ratio of works, what you are giving in, and what you are getting out, and what you are giving in. If all processes are reversible, so that's given. So Carnot cycle, so it means it's all are reversible. So the assumption, that's underlying assumption. So you need to ask to find out thermal efficiency and the work ratio, turbine work to compression work. The other one minus of the other ratio will be the work ratio, but here it's turbine work to the compression work. So we have said that neglect the changes in kinetic energy at inlet and outlet of turbine and pump. So it's just to simple that as steady flow energy equation to find out that work. So they asked to neglect kinetic energy and at inlet and outlet. So how do you calculate? I think you can solve. I'll give you some a simple question, 2-3 minutes. Yeah.
Can I ask one question, sir?
Yes.
Actually, Carnot steam cycle is impossible to in the practical, sir.
Yes.
Why we need study this, sir?
So just compare. See, to you have a Rankine cycle as well. So this is the ideal possible cycle which you can have. So you need a base benchmark, right? Carnot cycle is the highest efficiency cycle which you can have. It's ideal reversible. So that is the benchmark. So what you try, if you are trying to improve the efficiency, the maximum which you can improve is still the Carnot cycle. So that you need to understand that benchmark. So that's why we are studying that.
Okay.
I think first question is directly given down.
Yes, yes.
So I think you have some data. Sorry, I'll think I'll give for second question. I'll give you the data. Uh, these are the data which is all needed.
Yes, sir. In this problem, we need steam tables.
Yeah. So I have given all the tape. I have calculated everything and I have put up a slide. So you just need the vapor and you know that the 300 degrees Celsius and 20 degrees Celsius as the operating temperatures. So from TS diagram you can see that you can find A and B. Those are uh, vapor vapor state and the liquid state at saturated vapor and saturated liquid conditions. And you also know that this being reversible compression and reversible expansion, adiabatic expansion. So your entropy isentropic process. So your entropy will be same. So SB will be equal to SC, and you have the same for A and D. SA will be equal to SD. So using that you can calculate what is the dryness fraction uh, in state D and C using that entropy values, and you at G and SH you know you can calculate that saturated vapor in entropy and liquid saturated liquid entropy at 20 degrees Celsius. So using that you can calculate the dryness fraction, and using dryness fraction you can calculate the corresponding enthalpies. So here you know previously you know SD, you know SG, SH. Using that you calculate XC, XD, and same for XC. And enthalpy at this point is just vapor plus X into H, the difference H G minus HS. So that's what is begin given. You can calculate HC and HD. So you know all the enthalpies here now. So you know HB is 2749. I think HA is missing. I guess. I think somewhere I missed. Okay, I'll add that. Okay, so you know all
Where
the
is the
yeah
HFD, sir?
HFG. Uh, can HFG for what? HE, the first T2 or T1?
T1, sir.
Okay, I'll add that. Can take this HCH, HD is there, B is there. You need HA. Okay, anyway, I've missed that HA value. I'll add that, and also HFG value I'll add. And so I'll see that you know that efficiency of a Carnot cycle is 1 minus the higher lower temperature by higher temperature, sink temperature by source temperature. You can say 1 minus T1 by T2. We know T1 and T2, so we substitute this in terms of Kelvin. Uh, so we add 1 minus 20 plus 273, this is 293, and 300 plus 273 is 573. So this comes out to be 0.489. So this is the maximum efficiency which you can achieve uh, between that temperatures. So you can say if you give a 1 kilowatt of energy, the maximum work which you can obtain from that temperature levels is 0.489 kilowatt. You cannot achieve more than that. So that's what you can think in terms of Carnot steam cycle. So your cycle will always have this value lower than that. So this being a reversible cases, this is the maximum. So the rest of it will be this is the maximum exergy also, you can say. If you the 20 degrees your ambient condition, so this is the maximum exergy. So the actual one is in any cycle will generate will be very less compared to what you are seeing here. So the first part is calculated. You know HB and HC, which is 2749 and 1669. So that is 1079 kilojoule per kg. So that is the turbine work, and the work of compression is 1344. Compression is A and D. So you know for D 950.8 and A is 1344. So that difference is 393.3. And we have been asked to calculate the ratio of turbine work to the compression pump. So that will come out to be something around 2.75. So you are getting 2.75 times more work which you are in terms of work, and the work which you are giving in pump, you are getting 2.75 times more work out in turbine. So I think if you can calculate what will be the work ratio, what do you think the work ratio will be? And work ratio is the difference in the network by turbine work. Turbine work, network is turbine work minus the compression or pump work. So it will be 1079.6 minus 393.3 divided by 1079.6. So that will come out to be 0.635. So moving on, we have a heat engine which receives 100 kilowatt heat from a source at a temperature of 1000 Kelvin. So the heat engine produces a net power output of 30 kilowatt, and the heat is rejected to an environment with a temperature of 25 degrees Celsius. So write the overall mass, energy, entropy and exergy balance equations, and calculate the amount of heat rejected to the environment, calculate the amount of exergy destroyed and exergy rejected to the environment, and find the energy and exergy efficiency of the heat engine as well as the Carnot efficiency. So I have taken this link to exergy because the previous week someone had a question on exergy. So I have taken a problem combining both exergy and the Carnot one. So can try to solve this. So a heat engine receives 100 kilowatt heat from a source at a temperature. We have, uh, we are operating a heat engine. So the source is at 1000 Kelvin and it receives 100 kilowatt heat. So Q in is 100 kilowatt. It's producing 30 kilowatt work. Uh, so that is known, and it is rejecting it to an environment which is at a temperature of 25 degrees Celsius. So that the sink temperature, the amount of heat you are getting and the amount of source temperature and the power you are generating. So this could be any heat engine. You are not specifically telling which kind of engine is there. It could be any engine, and we have to compare it with a Carnot cycle to see how that is differing. So we have first is you have to ask to calculate write a overall mass, energy, and entropy and exergy balance, and then calculate the amount of heat rejected to the environment. I think that is fairly easy. You can use the first law, and C, calculate the amount of exergy destroyed and exergy rejected to the environment. D, find the energy and exergy efficiency of the heat engine. Exergy efficiency is just the efficiency of the cycle divided by the Carnot efficiency. It's just to comparing how much how is your efficiency compared to the Carnot efficiency, to get the idea of that. And energy efficiency is a normal efficiency, and is what is the Carnot efficiency. I'll give you 3-4 minutes. You can try to solve it. You can see the solution later after that.
Sir, efficiency is equal to 0.75, sir.
Okay. Efficiency of the cycle, is it?
Yes,
I think
0.7.
0.75 looks higher.
Very high, sir.
Is it Carnot efficiency or the cycle efficiency?
Cycle efficiency.
Okay. We'll see the solution. I think you can try the other
Okay.
things also. I think maybe what you can do is better calculate the Carnot efficiency and see what your efficiency is. So you'll get an idea.
Okay.
Carnot efficiency you have to be careful because one source temperature is given in Kelvin, the other is given in degrees Celsius. So you have to convert everything in Kelvin and use. So may I know how much did you get Carnot efficiency?
It came very high, sir. 0.95 something. I did wrong.
Okay, we'll see how the solution is. Then I think you can then revisit what mistake you are making. Okay. So first case is we have been asked to find out the mass balance, energy balance, entropy balance, exergy balance. So that's what is listed here. As we don't know anything about the components of the cycle, this is for the whole cycle. So assuming it's a closed cycle, the mass will be constant throughout in a total system. And then an energy balance, you know that there are three things happening in the system. There's a net work out which is coming, or you can say the turbine. There is no work input, so you can tell you that work output is same. And then there is a heat addition and heat rejection. So that is the energy balance. So Q in which is coming on, which will be equal to the Q out which is going and the work which you are obtaining. So that is the energy balance you will get. Or you can write it in terms of Q net equals to W net also, because this being a closed cycle, Q net will be equals to W net. So Q in minus Q out will be W net. I think it will solve one of the other questions also. And the entropy balance you can do is work will not generate in any entropy, so that will be 0. Q in this being at 1000 Kelvin, assuming that happens at the same constant temperature. So Q in by Th plus there will be some entropy generated, which will be equals to Q out by the lower temperature, ambient temperature, which is so that is the entropy balance. So if this would have been the Carnot cycle, that Sgen will be 0. The others will will be equal. Will become. You can also relate it to a Clausius inequality. So that is the entropy balance. Then exergy balance, you have some Q in. So that is the input which you are giving out of the cycle. You have one input and two which is rejecting work and Q out. So 3. So each will have its own exergy. So what you are giving in Q in will have some exergy. That is the maximum exergy which you can get out of that energy at that temperature and that Q value. So that is represented as x Q in. So this, how will you write? Q into 1 minus the T naught ambient temperature by the T temperature at which that heat transfer is happening. So that is xq in, and that is the work which you can get. So this work is distributed or in the other terms. So out of that you are getting some W out. So that will be equal to W net. So assuming that you are getting 100 watts or 100 kilowatts of exergy from that Q. So out of which you are getting 30 out. So from there, so just for thinking, the numbers may not be same. So you are giving 100 kilowatt. So that 100 kilowatt will be you will get some amount of that 100 kilowatt. It will be less than 100 kilowatt. So out of that you are getting 30 kilowatts out. Then you are rejecting heat to the ambient. So there will be some EXQ out. So we have to calculate Q out to calculate the EXQ out. So then the formula will remain same. Q out into 1 minus T naught by the temperature T at which that heat transfer is happening. And out of this process, some due to friction and other irreversibility, some amount of exergy will be destroyed. So that is represented as EXD. So this is the all balances which has been listed. So next is we have been asked to calculate the amount of heat rejected to the environment. Is the first part clear? If you want me to explain, I can explain it again.
Yes, sir. Yes, sir.
Okay. So the next part is you have to need to find out Q out. As I told you from the energy balance or the first law, you know Q net is W net, and you know W net is 30 kilowatts. And you also know the amount of energy heat which you are giving in 100 kilowatts. So the Q out will be 70 kilowatts. So this would be simple. Q out equals Q in minus W net. So 100 minus 30 is 70 kilowatts. So you are taking in 100 kilowatts, you are rejecting 70, and out of that you are getting 30 kilowatts out. So this is from a first law point of view. We'll see the next in from terms of exergy or what is this. So the third question was calculate the amount of exergy destroyed and exergy rejected to the environment. So that is the part C. So what we understand from part B was, we know that we are giving 100 kilowatts of heat energy in terms of heat, and we are rejecting 70 in terms of heat to the ambient, and 30 is we are getting in terms of work. As you can see,
sir, please explain exergy balance.
okay, I'll that's what I'll come. So thinking that you have a heat source, this is at 1000 Kelvin, so you are getting some 100 kilowatts of heat from that, correct? So the second law states that you cannot convert the whole amount of energy or heat to work. So that's what the second law says. So you cannot convert this 100 kilowatts to 100 kilowatts of work. So the maximum amount of work which you can get out of it is called exergy. So from that 100 kilowatts, when you run a process, ideal cycle, so if you run a maximum efficient cycle is a Carnot cycle. So if you run a Carnot cycle from 1000 Kelvin to the ambient condition, what amount of work you get from that is the exergy, or the maximum work which you can get from that source. So if you see EXQ in, so that is 1 minus T naught by TH into Q in. If you see that first term in bracket is the efficiency of the Carnot cycle running between that source temperature and the ambient temperature, okay, and Q in, because this will be equal to W by Q, so you multiply by Q to get the work. So that work is the maximum work which you can get from the heat which you are supplying. So it's assuming that it's all ideal, reversible, everything, this is the maximum amount of work you can get. And so you are having this maximum possible work. So this is the ideal case which you can have, but our process cycle is not ideal. So this is cycle is some other, which has some irreversibility and it has some friction, everything. So it is generating only 30 kilowatts out of it. So you have some exergy out of it. A part of exergy is you are getting it as a work. So and you are rejecting some heat. So this heat will also have some exergy. If you are rejecting it at higher temperature, so you will have some, you can also use that, run a cycle and get some exergy out of it. But if you are rejecting it to ambient, that means it doesn't have any exergy. So you have the maximum possible work, you are getting some work. So the difference is that you are having, because of irreversibility, you are destroying that exergy. So you are not getting that exergy out of it. So that is the exergy balance. If you see, Q in is the energy which you are giving in, the exergy of that. Exergy is the maximum possible. This is everything in terms of work. Exergy means you are converting everything to work, because work is that the highest quality kind of energy. So Q is written in terms of work. The amount of work which you can get from that Q in, maximum possible, equals the maximum possible work you can get out of the heat rejected, and the maximum work you are getting in, and the exergy work which you are destroyed. So that is the exergy balance. So in this case, if you see that your exergy in is 1 minus 298, because the question gives that the ambient condition is 25 degrees Celsius. So 273 plus 25, 1 minus 298 by 1000 into 100. So that is the maximum possible exergy which you can get. It will come to 70.2. So that is the exergy which you can get. And then you have exergy out. Q out is the exergy related to the heat which you are rejecting to the ambient. So being rejected to ambient means you cannot run any temperature, any cycle between the, there is no temperature difference basically. So your T naught by T bottom T is also T naught. So this will be 0, it will turn out to be 0. So the exergy out because of the heat rejected is 0 in this case. And the net work is the work you are getting. So that is 30 kilowatt. And because the cycle is not the ideal cycle, or it's not reversible, this will have some irreversibilities, and that irreversibility is generating this exergy destruction. So out of that 70.2 kilowatt exergy which you can get if it's running as an ideal cycle, Carnot cycle, you are generating only 30 kilowatt, and the rest 40.2 kilowatt is getting destroyed. So that's what this is getting, this equation is saying. So you have 70.2 kilowatt amount of work hypothetically running an Carnot cycle you can generate, but you are generating only 30 kilowatts with your cycle. So the rest 40.2 kilowatt is destroyed. So that amount of work which you could have extracted is now because of irreversibility you are lost. I hope this is clear.
Yes, sir. Clear, sir. Where it is we are losing this
See,
type of energy, sir?
see, normally this is because of friction and other practical this thing. In terms of heat or something, you lose to the environment. You are putting in work to overcome that friction and other stuffs. So in that process, you are losing this 40.2 kilowatts. You can say that ideally your turbine should be reverse isentropic, right? But it will not be. It will be some 0.8% or 0.7%. So you are losing some amount of energy there as well. So this small steps keeps on adding, and that is all the work will add, and it will be accounted in the destructed exergy. Okay, you got my point?
Yes, sir. Yes, sir.
Okay. So
Sir, if
yeah,
we need to decrease the XSD,
yeah,
EXD value, sir,
yeah.
what
If
we will do, sir? There?
see, that's what you need to have a high efficient compressor, and see, you need to reduce friction in usage. That is, you can only reduce it to possible listening, and you need a more high efficient compressor, and you need a bigger heat exchanger. Or you, because you can only try to reduce it, because you cannot totally get rid of it, because you will have exergy generated, entropy generated in heat exchanger, because heat transfer is happening between a temperature difference, because heat transfer will only happen between if there is a temperature difference. So if you are reducing that, then your heat exchanger size will go up, and if you heat exchanger this thing, that other problems will come in. So that you can only take it to some extent.
Oh.
Okay, so I think this is clear.
Yes,
So
sir. Clear.
yeah, so moving on, we have part D, so which says find the energy and exergy efficiency. So we can also say it as first law efficiency and second law efficiency. Also, some say the first law efficiency or the energy efficiency is W net by Q in, the amount of work which you are converting from the energy which you are giving. So 30 kilowatt by 100 kilowatt is 30%, 0.3. I hope this is clear. I think you made a mistake here, right? You need
Yes,
see
yes, sir.
efficiency is W net by Q in, the amount of work you are getting out with the amount of energy you are giving in. So that is the efficiency. So that is 30%. And exergy efficiency is W net by exergy in. You can calculate it that way, or the other way around is you can calculate the efficiency by Carnot efficiency. So you can EXQ in is the maximum amount of work which you can get out. So W net by maximum work which you can get is second law efficiency. So W net is 30, and the maximum efficiency is the work you can get from Carnot cycle. So 30 by 70.2. So this will be 70.2, the bottom part, which will come out to be 42.7%. So as you can see that your cycle is just close to 50%, operating at 50% efficient as the Carnot cycle. So that's what this says. It's like your cycle is 40% efficient compared to the Carnot cycle with respect to the Carnot cycle. So that's what the second law says. It's just a comparative exergy. So if this being 100%, that says your cycle is the base cycle. It has reached that Carnot efficiency. You cannot go more than that. This first law efficiency, that W net by Q in, energy efficiency can never be 100%. But this exergy efficiency theoretically can be 100%. If you are operating as a Carnot cycle, this can go 100%. So this exergy efficiency can be greater than the energy efficiency, but practically you may not find that. Okay, so moving on. So I've given this diagram comparing the both. So this is the first law kind of diagram. You have QH in, heat in coming in, and you have W net going out, and QL is the heat rejected. So this is the general first law in terms of energy coming in. So the second law, if you see, there's exergy coming in with respect to the heat transfer QH, and then there's some exergy lost because of heat transfer to the ambient, and then W net is the work which you are getting, and there's also exergy which is EXT, which is the exergy destroyed. So the exergy coming in will be equal to the exergy which is going out. So that is the exergy balance equation which we saw, and the fraction of this exergy which is coming in is distributed across the other exergy which is going out. So that amount of fraction, 30 kilowatt, is what you are getting W net. And as I said, in reversible Carnot efficiency, Carnot efficiency is you know the source temperature 1000 Kelvin, and you also know the ambient condition 25 degrees Celsius, which is 2098 Kelvin. So the efficiency of Carnot cycle is 70.2%. If you remember, exergy destroyed, which exergy in which is coming in, was calculated is also 70.2 kilowatt, because the amount of energy coming in is 100 kilowatt. So 70.2% is 0.702 into 100, which will give you 70.2 kilowatt. That is the exergy coming in, which we saw here in the option C while solving. And the other way of calculating the second law efficiency or exergy efficiency is efficiency by efficiency of Carnot. It's 30 by 70.2 is 42.7%. I hope this is clear.
Yes, sir. Clear, sir.
Okay, so I think this would have given a fair idea about what is exergy and how the cycle is compared to the Carnot cycle. Everything I think the single problem would have deal with that. Okay, so moving on, we'll take a Rankine cycle. A Rankine cycle, this being a simple process, and another reason for why we you asked the question, right? Why we need to study Rankine cycle as a Carnot cycle. See, here this comparison exergy efficiency we are comparing with this Carnot cycle. So Carnot cycle is the maximum possible efficiency which you can get. If you see it, in this example, this cycle is just 42.7% of the Carnot cycle efficiency. So what we can see that there is scope for the cycle to be improved. You asked, right, how to reduce exergy destroyed. This exergy destroyed, if you are reducing, then your cycle is becoming more efficient. So your efficiency and second law efficiency will all go up. So this gives a comparison, and it can work on the cycle to see how we can increase the efficiencies of cycle. So that I think will come in the next week course. So the Rankine cycle, how to make it more efficient, and to deal with that will be in the next weeks. So that will give you a fair amount of idea why to deal with why to see with respect to Carnot cycle.
Okay.
Yeah. So we have a problem on Rankine cycle. So here we have a compression and expansions are adiabatic. So this is all ideal Rankine cycle. That's the case here. So we have reversible adiabatic cases, and we have said that kinetic and potential energy are negligible. So for that simplification of steady flow energy equation assumption. So the dissipation is neglected, and steady state results in steady state operation. So that are the assumptions we are making. So we have a data given that maximum pressure is 40 bar. So you can say that P2 is 40 bar, and temperature given at point 1 is 35 degrees Celsius, and temperature at point 2 is 35.14 degrees Celsius. So we know two temperatures, and the average specific volume of liquid water is also given as 1.0043 10 power minus 3 meter cube per kg. That's a specific volume is given, and water mass flow is also given. Mass flow of water is 7 kg per second. So the data is also provided for the saturated properties for states, the corresponding pressures, 40 bar and 35 degrees Celsius condensing temperature. Sorry, evaporating and condensing temperature. And you need to calculate the thermonic state points at point 2 and 4, and work and heat transfer in all of the processes, and the efficiency of the cycle. I think the data is everything is given. I think you can try once, and we'll see it in. I'll give you 2 minutes.
Sir, please explain the first question, sir. Calculate the thermodynamic state at point
Yeah,
1.
you need to
What
calculate.
we will use?
Yeah, you need to calculate the enthalpy and entropies at these state points. Okay, we'll see how this to be solved. So we need to find, first question is we need to find the state points of 2 and 4, because we know 1 and 3 from the saturation table which is given, states of water. We know 1 and 3. 1 is at 35 degrees Celsius temperature, so it's at 0.0562 bar. So 35 degrees is the normal ambient condition temperature, so that's what is given. And you know that maximum pressure is at P3 and P2, that pressure is 40 bar, so that table is also given. So you know 3 is enthalpy, the vapor enthalpy 2565, sorry 2800, and 1 is the saturated liquid enthalpy H dash, it's 146.56. Okay, so we know 1 and 3, we need to calculate 2 and 4. So we'll see how to calculate state point 2. So for state point 2, we know that this is what 1 and 2 and 3 and 4 are reversible adiabatic process or isentropic process. So entropy will be same. We know S2 equal to S1, and from there, if you want, if you can use a steam table, or you need a subcooled condition. So if you have a chart, you can calculate 2 directly, or if you don't have, in this case we don't have. So but what other detail we have is, we know the specific volume of the liquid, and we also know the pressure differences, the maximum and minimum pressure in which the pump is operating. So the work done in the pump is equals to V into or minus integral V dP. So that will come out to be V is will not vary much, so it will become constant. So you can take it constant, so it will be V integral of dP, which is the difference in pressure. So the specific volume into the difference in pressure, which will give you 4.017 kilojoule per kg. Okay, if it would have been volume, this would have been in kilojoule, and this would have been the m dot into delta H, but this being specific volume, this is in specific enthalpy. So the enthalpy at point 2 is, you can say, which is H2 minus H1. So we know that delta H, so it's just H1 plus delta H, which will come out to be H1, we know from the table 146.56, and we have calculated the delta H is 4.017, so this will be 150.57. So that is the enthalpy at point 2 that we have calculated. And we have also know for state 3 and state 4 the entropies are same. So from here, and we know at 4 we need to calculate the dryness fraction. So we know the entropy at 4, we know entropy at vapor and liquid saturated conditions. From the table you can calculate 0.5049 and 8.35. So you can do a balance, and we can find out the dryness fraction at 0.4. So it will come out to be 0.709, and then using that we can do an enthalpy, we can substitute vapor plus dryness fraction into the latent heat enthalpy. So H4 into will be equals to 1861 kilojoule per kg. So that is also known. So we have calculated all enthalpies at all 4 points, and we know corresponding temperature, pressure and everything. So the second question is, calculate the work and heat transfer during each process. So process 1, 2. So you can see process 1, 2 is for pump, 2, 3 is for boiler, 3, 4 is for turbine, and 4, 1 is the condenser. So 1, 2 is a pump, so there is no heat transfer, so Q is 0, and work is M into H2 minus H1. So we have already calculated delta H 4.017, and we know mass is 7 kg per second from the question. So if we substitute 7 into delta H, which will come out 28.1 kilowatt. So this is for pump. So process 2, 3 is boiler. We are supplying in heat, but there is no work, so work is 0. Q in is m dot into H3 minus H2. So here too we have calculated all H3 and H2 values. So we on substituting, we get 18548.1 kilowatt. So this is the amount of heat which you are giving in. So it will be close to 18.5 megawatt. So process 3, 4 is the turbine work. So turbine work m dot into H3 minus H4. So H3 minus H4, it will come out to be 6575 kilowatt or 6.5 megawatt. So you can say there's one third of what is being converted, the energy which you are giving is converted to work. Process 4 is 4.1 is condensing process. Here too there is no work output, but you reject heat. So the Q out is m dot into H4 minus H1. So from there you can know it will come out to be 12 megawatts. So we have calculated all work and Q. So now we can calculate the efficiency. So efficiency is W net is W net is turbine work minus pump work, which is 657.5 minus 20.8.1. So we see this is we can that assumption of taking that pump work negligible. I think one of the problems it was stated, assume that pump work is negligible. You can see you are getting 6,575 kilowatts, but you are consuming only 28.1 kilowatt. So that assumption you can say fairly valid. So 6575 minus 28.1 will give you W net, and the Q in is 548 kilowatts. So on substitution you'll get efficiency as 35.3%. So this is the efficiency of the ideal Rankine cycle operating between 250 degrees Celsius and 35 degrees Celsius. So if you see Carnot efficiency, it will be larger than similar to what we saw in the previous problem. There too we got 30% efficiency. Here we are getting 35.3% efficiency.
Sir, here mass is not given in the problem, sir.
It's
How do
given
you find the process?
mass is given as 7 kg per
Uh,
second.
o- okay.
Okay. Okay. Any other doubts?
No, sir. Okay, sir.
Yeah. I think I finished my problem, so that's it. I finished what I have prepared for today. If you have any additional doubts, you can ask.
Okay, sir. No doubts, sir. Sir, can you share this
Yeah, it will be.
problem?
Yeah, it will be added in the site. You can go in that NPTEL site where you're seeing. It will give you a link. It will be added. You can refer there.
Okay, sir.
Okay then. Okay, then
Thank
I
you,
think
sir.
we can close the session.
Okay.
Thank you.
Thank you, sir.
Thank you.